Hi everyone. Today we are going to discuss algebra and the use of letters. So to start off, you've probably heard of the term algebra before. It actually originated from a book that was written in the 9th century, so around the year 900. You know how we're in the year 2022? And we're in like the 20th or 21st century. It was written in the 9th century, so around the year 900. That's how old algebra is. And the word algebra is a translation from the original word that means putting together, different pieces. So it's kind of like you're putting a puzzle together. So algebra, when we use it in math, we actually use letters because we have some pieces of the puzzle that are unknown. Okay, so you'll see that there are letters being used to represent what we don't know. We have pieces of the puzzle that are missing, and we're trying to figure out as much as we can here. All right, so let's suppose that we go shopping and we're looking for hats and t-shirts. And in the store, the hats are $10, good price, and the t-shirts are on sale for $8 each. We want to know what's the total price that you would pay if you buy one hat and 4 shirts. If you bought one hat, you would take that $10 and you would add it to the total price of the shirts, right? Each shirt is $8. I'm going to put these in parentheses so we know that 4 is being multiplied by 8 together. So we have $10 for the hat plus 4 times 8 because there's 4 shirts that we want to buy. So that's going to be 10 plus 32, and that's going to be $42. Okay? What is the total price if you buy one hat and 6 shirts? Well, again, one hat is $10. We're going to add it to the total price of our shirts. Each shirt is $8. We're going to pay that price 6 times. So we multiply 8 by 6. We get 10 plus 6 times 8 is 48. So that total is $58. So remember, we're trying to figure out this puzzle, and we notice that there is a pattern. So algebra is all about sniffing out the patterns. We notice that we're constantly adding $10 for one hat, and we are adding that to however many t-shirts we want, multiplied by the price of each t-shirt. So now for the next question, the last question, they're asking you, what is the total price if you buy one hat again? These were all asking for one hat. So we're going to follow that same pattern, 10 plus, because we're always talking about one hat. And now it's N shirts. So you notice there's a letter that's being used to represent, like we said, the unknown. We have no idea what that number is. We usually see N represent number, but they could have used any other letter like X or Y or A or B. But they don't know how many number of shirts there are, so they're putting N instead. Well, we can still come up with an expression for that because we figure out the pattern. Every time we added 10, and then each time we took the number, the first time we knew the number was 4 shirts. Second time we knew the number was 6. This time we don't know what the number is. That's okay. We're going to do the same thing. Take that number, we don't know what it is, it's unknown for now, and multiply that by 8, the cost. So we're just following the same pattern. This time we're just replacing the number, which we don't know, with the letter, or we call that the variable, N. And then we can rewrite this as 10 plus. We don't want this X here to represent multiplication because now that we're using letters, we might confuse that as the variable or the letter of X. So we're going to just smush the 8 and the N together. Whenever you see a number and a variable, a letter next to each other, you can assume that that means multiplication because again, we don't want the x for multiplication to be confused with a letter x. So we're just going to smush them together and know that this really means 8 times n. So the pattern was we always added 10 to whatever amount of shirts there are times 8, which was the amount for each shirt. So in the above example that we just talked about, the letter n in 10 plus 8 times n, and again, we're trying to avoid this multiplication sign here, may take on the value of 4 or 5 or any whole number, right? Because we're talking about shirts, it can't be fractions. So that n can represent any whole number. So we call the n a variable instead of saying letter. And we call it a variable because this unknown amount can vary. It can change depending on the situation. It can one moment be 1 shirt and another moment be 10 shirts. So that's why we call it a variable. It's never going to really stay the same amount. And then this entire expression consists of numbers, letters, and operations. This is called an expression right there. Okay? So the letter is called the variable. The entire kind of sentence or phrase that includes adding, subtracting, multiplying, dividing, numbers, and variables is called an expression because we're using it to express what's going on in a situation. So these 2 words should go into your notebook: algebraic expression and variable. Variable is a fancy word for the letter that you're using to represent an unknown, and expression is this entire group of numbers, letters, and operations that are working together to express what's going on in a situation. Okay, so there are special words or vocabulary that you'll need to remember for addition. When we are talking about addition, we could just simply say add A to B. Or we could use that special word sum. Sum also says that we're adding the 2 numbers together. For subtraction, we could say subtract, or we could use the special word difference. Difference also tells us that we want to figure out the subtraction answer, because by subtraction, we'll figure out which one is higher and by how much. For multiplication, again, we can say divide, or we can use the special word product. Product also tells us that we are trying to figure out the answer to a multiplication problem. Okay, and remember with multiplication, instead of writing the times symbol, which again looks like the variable x, we can just smush those 2 together. So GH just means G times H, or H times G. For division, we could say divide, or we could use the special word quotient. Okay, and just like with multiplication, we like to get rid of this division symbol. So sometimes you'll see it. It doesn't bother us too much because it doesn't look like a variable of x. But we also like to write with a fraction bar. So x over y is the same as x divided by y. So all these kind of important terms and concepts that I underlined or circled, you should probably put into your notebook so that the next time you see 2 letters, 2 variables smushed together, or 2 variables in a fraction with a fraction bar between them, you're not confused. You know that's just another shorthand way of writing multiplication or division. All right, let's move on then. So talking about exponents now. Can we use variables with exponents? Yes, we can. So if I'm multiplying a, the variable a, by itself twice, I could just say a squared, or a to the 2nd power. If I'm multiplying b, the variable b, by itself 1, 2, 3, 3 times, I could also say b cubed, or b to the 3rd power. C times c times c times c, I could say c to the 4th power. D times d times d times d times d, I can rephrase it and rewrite it as d to the 5th power. Okay, but be very careful. We've talked about this before when we talked about exponents. Exponents are repeated multiplication, okay, not repeated addition, which is what some people get confused with. It's repeated multiplication. So a squared is not the same as 2 times a, because 2 times a is you're adding it 2 times. B cubed is not the same as 3 times b, because that means you're adding b 3 times. B cubed is b times b times b. So be very careful that you know the difference between your exponents and then simply multiplying by a number, because that would just mean repeated addition. Okay, let's do some work as practice. So let's look at example 4 in your book. This says that we need to simplify the following. A wants us to simplify b times 1 times c times b. B wants us to simplify 7x times 2y times y times y. That's already annoying me because I can't really tell the difference between multiplication and a variable. And C, p divided by q times 3. So go ahead and pause the video and try that on your own first. Okay, so let's take a look at A. We have 2 b's that I notice, so I can change that into b squared, and then we have a c. Remember, we don't like the multiplication sign in between, that x, because it's going to look like a variable of x. So I end up with b squared times c written with it smushed together. I am going to get rid of that times 1 because remember, it doesn't do anything for me, right? Anything times 1 just stays the same. So that's extraness. Whenever you have a times 1, you can just kind of make it disappear into the background because it doesn't change anything. So again, I have 2 b's, so that becomes b squared. And then I also multiply by a c, so I add the c right there. This kind of just assumes that it's multiplication because there's no sign in between. Okay, let's look at part B. Okay, I have numbers, 7 times 2, so I can change that into 14, right? Because I want to simplify. And then I have x's. Let's count how many x's. There's 1 and, oh, that's it. So let's put down x. Okay, that's the variable, not the multiplication. And then let's see how many y's there are. There's 1, 2, 3 y's. So y to the 3rd power. So this is 14 times x times y to the 3rd power. I got rid of all those x's in between for multiplication. The 7 times 2 I combined to 14, 1x and 3 y's. I changed to exponential notation. Last one, p divided by q times 3. Okay, so p divided by q, I know from what we just talked about that I can rewrite it as a fraction bar. P over q, that means the same thing. And then times 3. Ugh, I really don't like that multiplied by 3 because that looks like an x as a variable. So remember, any whole number really is over 1, right? Because this is like 3 ones. It doesn't change the number. We can multiply across. P times 3 would be 3 times p. We like to write the number first for order, and so we can see the number first. Keep that division bar. And then on the bottom, it's q times 1. Remember, anything times 1 stays the same. So we can actually rewrite it like this. 3 times p divided by q. Looks so much easier to do compared to this long thing over here. Because I already know I'm going to multiply by 3 and p together. It's going to be on top. And then I'm going to figure out whatever q is, that's going to be on the bottom. So then I got one kind of piece, right? That's simple and simplified for us. Let's do one more. Let's distinguish between 7x squared and the quantity of 7x, all in parentheses, squared. Go ahead and pause the video and try it on your own first. What's the difference between these two? Okay, so I have 7x squared. That looks good on its own, so I can keep it as it is. But let me try and simplify this right here, 7x as a quantity squared. I notice I have parentheses. So parentheses tell me that the 7 and the x go together. They both are together and being squared. So that means everybody inside has to equally be squared. They're kind of like a family unit. X can't get that power without 7 getting that power. One's going to get jealous of the other, right? They're part of the same family. So if we are going to give X that second power, 7's going to get jealous. 7's like, hey, I want that second power as well. I want to become a bigger number. Okay, so that's what that parentheses tells us. So what's 7 squared then? 7 squared is really 7 times 7. And then remember, we still have, I'm trying to draw my x's as small as possible, multiply by x squared. So 7 times 7 is 49. And then we have that x squared. So 7x, the quantity of 7x squared, is really the same as 49x squared. Don't forget, we still have to compare it to 7x squared. So how can we compare 7x squared and 49x squared? Well, it looks like they're the same because they both have x squared, right? They're both the same there. They both have x squared. The only difference is right here. 49 is really 7 times 7. There's an extra 7 being multiplied, while 7x squared only has one 7. So again, the x squared part is exactly the same. So really, the quantity of 7x squared is 7 times greater than 7x squared. That's the difference right here. That's how we can distinguish between the two. Other than that, they're exactly the same, except the quantity of 7x squared is 7 times larger because that 7 got that power of 2. All right, let's move on to one last problem. Express the following word statements algebraically. So we have the first one, subtract n from the quotient of m divided by t. Oh my gosh. So you want to write it as an algebraic expression with your symbols and your variables and your numbers. Part B, add the product of a and b to the square of c. Go ahead and pause the video and try it on your own first. So we have to remember our special vocabulary. So subtract n, okay, subtract n from something else. So that's why we're leaving this space in the front here. We're subtracting n from something else. From the quotient of m, quotient means to divide. Okay, the quotient of m divided by t. So we can rewrite it like this. M over t minus n. Subtract n from the quotient of m divided by t. That's a simplified way of writing it. Part B, add the product means to multiply, product of a and b, so we're going to multiply a and b together, so we'll just smush them together, to the square of c. To the square of c. There you go. We added the product of a and b, multiplication, answer of a and b, to the square of c.